Hello class and YouTube, my name is Christian Ballou and this is my presentation on my senior projects in design. I did a laminar flow tank feasibility study. So first for the agenda, we'll go over the introduction, the calculations used, the design of the tank, the budget, some lessons learned, and we'll wrap it up with a conclusion. So you might be asking yourself, why a laminar flow tank? Well, a laminar flow tank would be important if you wanted to scale a model, say such as a glider, a submarine, maybe even a ship. So if you wanted to scale that down and model it inside of a tank to see the fluid flow around it, turbulent flow wouldn't really be sufficient. This is because if you were to input turbulent flow into the system, you would not see very much difference between the turbulent flow before the model and after the model. This is why laminar flow would be important. That way you can see the fluid flow, how it reacts with the model, and hopefully you'll have some turbulence or flow separation that you'll be able to view inside the tank. So as an example, for just some different scale size that you might be able to model inside this tank, you can do an AUV glider at a 1:4 scale. Maybe you want to do a Virginia class submarine. You can do so at a 1:50 scale, or maybe even the longest ship ever built, the Seawise Giant, at a 1:500 scale. So next we'll go over the calculations used, and some of the calculations I used were similitude, Reynolds number, entrance length, the flow rate, some head losses, and the power needed for the pump. So the first equation that I used was similitude, and a little background on similitude is the relationship between a prototype, which would be your real world object, and your model, which is your scaled object. So you can use similitude with dimensionless parameters, and these parameters can be things like Reynolds number, the Froude number, your drag coefficient. In this case, in this example, I used Reynolds number, and Reynolds number was important to me because I was going to model a AUV glider, which is under the free surface, which Reynolds number is great for comparing. So in this case, I used a prototype velocity, which is the real world velocity of the AUV, at 1 meter per second and at a 1:4 scale factor. And it turns out that my velocity of the model is 0.25 meters per second. In other words, this is how fast my flow needs to be inside of my tank. The next calculation I used was Reynolds number. Reynolds number describes if your flow is laminar or if it's turbulent, or maybe it's in the middle in a transition region. So laminar flow is when flow is uniform in the same direction and velocity. The formula for Reynolds number would be rho VL over mu, where rho is your density, V is your velocity, L is your characteristic length, and mu is your kinematic viscosity. Using this equation, I calculated that my Reynolds number inside of my laminarizer is 794, which, as you can see in the bottom left text here, is in the laminar regime of the flow, which is good for this tank. Next, I calculated my flow rate, which I needed for my pump. And since I knew the cross-sectional area of my tank, which is 0.25 meters by 0.25 meters, I can get my area. And I also knew my velocity from the previous calculation of 0.25 meters per second. We use the formula Q equals AV, and I get a number of 0.015 meters cubed per second. Next, I would like to find the flow rate over my weir, which will be in the back of the tank. And you use the formula to calculate the flow rate over the weir, which is Q equals CLH to the 1/5 or 1.5 power, where C is your weir discharge coefficient, and that describes the shape of the crest of your weir. In this case, I used a sharp crested weir, and my coefficient is 0.29. I also have the length of my weir, the height of flow over my weir, the upstream depth of flow, and the weir height. And I come out to a calculation where my flow rate over the weir is 0.0057 meters cubed per second. Next, I would like to find how long does it take for my flow to become fully developed? And in other words, how long does it take for my flow to become fully laminar? This happens inside of my laminarizer, which will be in the front of the tank. It is responsible for taking turbulent flow and transitioning it into laminar flow. I use the entrance length formula, which is 0.05 times the Reynolds number times the diameter. And the diameter would be 0.003175. In other words, this is how small my pipes need to be inside of my laminarizer. And I get a number of 0.13 meters or 13 centimeters. Next, I would like to calculate what will my head loss be inside of my laminarizer. And as you can see, the cross section, these are those little pipes that will be sitting stacked inside of this laminarizer, responsible for it for taking transitional or turbulent flow and transitioning it into laminar flow. So for the head loss inside of a pipe, you need your roughness coefficient, your length, your diameter, your flow velocity, and of course the gravitational acceleration. And the value I get is 0.00225 meters, which is good for this project. The next head loss I calculated would be the head loss inside of the pipe coming from the pump, which is this right here. As you can see, the pipe connects to the pump, pumps it up to the front of the tank, and goes through the laminarizer over the weir and then recirculates again. And for this one, I got 0.0078 meters for this pipe. Next, I wanted to calculate what my power needed for my pump be. So I used the formula P is equal to gamma Q times HP, where gamma is your specific gravity or specific weight. Q is your flow rate, which was determined in previous calculations, and then your head of the pump. So, or in other words, how high your head needs to pump, or how high your pump needs to pump water. And I come up with a value of 54 watts, or approximately 0.7 horsepower, which is sufficient for the pump that I chose. Next thing I did was I used CFD, or computational fluid dynamics, specifically Autodesk CFD, and I use this to verify my fluid calculations and also to verify or visualize my fluid flow. So in this top model here is a model of my tank, and I did this to see the flow rate over the weir through the tank. As you can see in the test section, there's a free surface of water, and the water nicely flows over the weir. This is also represented in this 2D model here. As you can kind of see the tiny pipes of the laminarizer here, and it flows over the weir, the water does, and the blue is essentially void space, so the air. And this small bar down here is one of the pipes inside of the laminarizer. And you can kind of see how the flow fully develops inside of the pipe as it starts out very yellow in this regime and slowly transitions to a more red in the middle, which would signify that it is fully developed inside the pipe. Next up, we'll go over the design of the tank. The tank itself will be made of 3/8 inch acrylic, and this is good because it's clear and you'll be able to see what is going on inside of the tank. It'll be surrounded by an aluminum support structure to give it strength and rigidity. Also, the laminarizer right here will be in the front, responsible for taking your flow from turbulent to laminar. And there will also be a weir in the back of the tank, which is also removable. So if you wanted to run a test without the weir, you could. If you wanted to change the shape of the weir, you could. So how will you actually visualize this flow? Well, we're going to use a process called electrolysis, and I will have a platinum wire and I'll pass current through it. And this creates a small stream of bubbles, essentially splitting H2O molecules into H2 and O, which hydrogen and oxygen. And these bubbles follow the path lines of the fluid flow, and they're small enough to where they don't rise under their own buoyancy. So they will flow along your test object. Now, also we'll use a laser sheet, and this laser sheet will be made of lasers that will spin in a circle, and they'll be spun fast enough to where it'll look like a sheet of lasers, and this will illuminate the bubbles as they flow around your object, as you can kind of see in this example right here. So we'll go over the budget now. So for the tank itself, this is just the acrylic. We'll have a budget of $230, and the table, which will be made of this extruded aluminum profiles, will be the most expensive part of the budget at $1,225. The pump itself also includes this VFD, which is a variable frequency drive responsible of controlling the speed of the pump, at $1,160. The frame, which will also be made of this extruded aluminum profiles, this is the frame around the tank itself, will be made or will be $185. And the laser sheet, which consists of lasers like this, will be $235. The electrolysis, which will house this platinum wire, will be around $100. And then miscellaneous parts such as silicone, glue, hardware has a budget of $80. And the approximate total is going to be $3,300. Of course, these prices are subject to change with the cost of building materials now. So some lessons learned that I learned throughout this past year. Definitely needed to know or needed to learn these new calculations that I needed to design this tank. I learned how to use Autodesk CFD, which was how I used to verify those calculations and visualize my fluid flow. I also got to use Autodesk Fusion 360, which I knew how to do beforehand, but it was nice to learn or to hone my skills on it again. For soft skills, critical thinking was the one thing I used the most. I had wrong calculations sometimes, and I had to go back and find out why. And I had to correct those calculations and redo them many times. And so critical thinking was important. Also, each week we gave a presentation on what we had done from the previous week in this class, and we had to get up in front of our class and present our findings. And also each week we were assigned new tasks to do in the project. So learning how to manage those tasks with other classes and work and just general life was definitely important. The thing that surprised me the most was how long the research and design process actually takes. Going into this, I originally thought that it would take no more than a few months to design a simple tank. It turns out that designing a simple tank is not as simple as I thought it was. There's a lot of calculations I had to verify, a lot of calculations I had to redo. Research papers I had to read, see what other researchers had done in the past, and see what I could learn from them. So the R&D process takes longer than I thought it would. So these are some of my references used, like I just mentioned in the research papers. These papers helped me get a better understanding of not only fluid mechanics, but also how to build some flow tanks, also how to visualize flow around an object, as well as how to design some of these objects for certain criteria. So in conclusion, I learned from this project, and I've studied this project, that it is feasible to build a laminar flow tank, and you can test models in it with a flow velocity of 0.25 meters a second while using electrolysis and a laser sheet to visualize the fluid flow. And to reiterate, these models can be something like a ship or a boat on the free surface. It can be something, maybe a fish or an ROV, or just a general object such as a sphere or cylinder. Or as long as it's moving at subsonic speeds, you can, since my flow tank does not move at supersonic speeds, you could theoretically model Madi's favorite aircraft, an F-22 Raptor. So my name's Christian Ballou. I'm a senior at the University of Southern Mississippi, majoring in ocean engineering. And at this time, I will open it up to any questions. Thanks.